Hello everyone, I am Abhiram Pamula from Oklahoma State University. Today I'll be talking about life cycle assessment of switchgrass to jet fuel via a novel co-fermentation of sugars and gas. In this presentation, I'll be addressing the switchgrass to jet fuel pathway using an acronym called STJ. So, what is the motivation behind performing an LCA analysis to STJ pathway via a novel co-fermentation process? Transportation sector in the United States account for 29% of total greenhouse gas emissions in the year 2019 from fossil fuel combustion. In the transportation sector, aircrafts account for 9% of total emissions, which created substantial influence to investigate alternative fuel technologies from environmental perspective. In order to come to a reasonable conclusion, regarding which fuel process and usage contribute to fewer GHG emissions in the life cycle assessment is important and helps in accounting emissions in the fuel production process. When it comes to feedstocks, lignocellulosic biomass has the potential to produce butanol and is expected to play a significant role in potentially producing jet fuel. Lignocellulosic biomass, or LB like switchgrass, provides a renewable source of carbon and energy with potential to reduce environmental impacts of jet fuel made from butanol. Butanol can be produced by traditional acetone, butanol, and ethanol or ABE fermentation process using molasses and starches. New technologies are needed to enhance the conversion of LB to butanol and improve process feasibility. At OSU, Dr. Attier and his research group developed a novel co-fermentation technology to ferment both sugars, including glucose, xylose, and the gases evolved during fermentation. During laboratory experiments, the research group at OSU were able to improve the butanol product yield by over 15% when compared to traditional ABE fermentation. For more information on co-fermentation technology, please go through the references provided here. Finally, to gain important insights into process feasibility and benefits from environmental perspective, an LCA was performed at OSU. The figure here shows the system boundary used in the LCA of STJ pathway, where major inputs and emissions from the STJ pathway were analyzed in detail. Moreover, to compare the GHG emission contribution, different jet fuel pathways were assessed in the LCA. The LCA encompasses processes from well to wake, including feedstock production, conversion, and fuel combustion. Jet fuel production pathways evaluated include switchgrass to jet fuel or STJ via co-fermentation and traditional ABE fermentation routes, corn to jet fuel or CTJ, soybean to jet fuel or HRJ, conventional petroleum jet fuel or CPJ, Fischer-Tropsch jet fuel or FTJ. These pathways generate many co-products that require allocation. For reasonable comparison, all the co-products produced in the fuel pathways were allocated as per ISO 14044 guidelines. In the STJ pathway, the co-products produced include acetone, ethanol, electricity, gasoline, and diesel. The main goal of the LCA is to estimate the life cycle GHG emissions from STJ pathway via both co-fermentation and traditional ABE fermentation routes. After determining the emissions in the STJ pathway, life cycle emissions are compared with other alternative pathways. Data used to assess the fuel pathways are obtained from laboratory studies, literature, and from greenhouse gases regulated emissions and energy use in transportation or GREET model developed by Oregon National Laboratory. Moreover, the combustion efficiency was assumed to be similar for all the fuels compared in this LCA. Therefore, the functional unit used for comparison is 1 megajoule. Finally, all the results are presented based on 100-year global warming potential or GWP 100 expressed as CO2 equivalent based on the data obtained from Fifth Assessment Report of Intergovernmental Panel on Climate Change or IPCC. Furthermore, to understand the scope of the LCA, limitations and assumptions are listed such that Emissions from handling microbes during fermentation are excluded from the LCA and assumed to be small. In addition, emissions from infrastructure of the fuel refineries are neglected because they are assumed to be similar for all the fuel pathways compared. When it comes to carbon sequestration, temporary sequestration in biomass and soil are assumed to be in steady state. Finally, while the impacts of direct land use change are included in the current LCA, the impacts of indirect land use change is considered beyond the scope of the analysis. In STJ pathway via co-fermentation, the unit processes from well to wake includes fertilizer production, switchgrass farming, pretreatment and hydrolysis, co-fermentation, separation of ABE with distillation, butanol to jet fuel conversion, and combustion. Out of all the unit processes that contribute to life cycle emissions in the STJ pathway, pre-treatment and hydrolysis contribute to more than 50% and major chunk of the life cycle emissions as shown in the figure here. Moreover, energy-intensive unit processes including distillation and farming also contribute to significant number of emissions in the STJ pathway via co-fermentation route. To assess the impacts of farming on the STJ pathway, spatial variability in switchgrass yield and nitrogen fertilizer application was used. Sensitivity of GWP 100 across different geographical locations is important because the soil properties, weather patterns, nutrient availability will vary at different places. The data used to assess the GWP 100 variability across regions in the United States include Oklahoma, the Corn Belt, Maryland, Iowa, and Illinois. Data representing Corn Belt includes average across regions in the Midwestern United States that are dominant in corn production. Life cycle emissions were estimated during the establishment year and after first cut, which were compared based on weight basis of switchgrass harvested. In the geographical location used for comparison, co-fermentation seems to significantly reduce life cycle emissions in the STJ pathway, irrespective of the yield and nitrogen fertilizer management. There are alternatives for the processes that can be used in the STJ pathway. As mentioned earlier, unit processes including pretreatment and hydrolysis, ABE separation including distillation, and farming are the most significant contributors to the life cycle emissions in the STJ pathway. Efficient pretreatment technologies can reduce life cycle emissions in the STJ pathway. The STJ pathway assessed in the LCA has unit processes including farming, dilute acid pretreatment or DAP, sugar hydrolysis, co-fermentation, distillation with heat recovery, butanol to jet fuel conversion, and jet combustion. As an alternative to DAP, ammonia fiber expansion or AFIX pretreatment technology can significantly reduce life cycle emissions in the STJ pathway. Next to pretreatment, distillation with recovery of heat was able to significantly reduce GWP 100 in the STJ pathway via co-fermentation route. To examine the importance of ABE yields and its effect on GWP 100 in the STJ pathway, a sensitivity analysis was conducted using base yields or reference yields. Base yields used for STJ pathway via both co-fermentation and traditional ABE fermentation routes are 0.321 gram ABE per gram sugars and 0.278 gram ABE per gram sugars. Effects of ABE yield on GWP 100 in the STJ pathways were assessed by plus or minus 20% change with respect to base yields. Changes in input assumptions that modified life cycle by more than 3% were considered to be sensitive for both traditional ABE fermentation and co-fermentation routes in the STJ pathway, and these results are shown in the figure here. The most sensitive input parameters for the STJ pathway, as shown in the figure here, were natural gas and ammonia in both hydrolysis steps and switchgrass farming. 6 different fuel pathways were compared to make an assessment on STJ pathway and its environmental impact in the fuel production and usage. The life cycle GWP 100 for the STJ pathway has 4 scenarios, which were compared with other alternative pathways including corn to jet fuel or CTJ, soybean to jet fuel or HRJ, Fischer-Tropsch jet fuel or FTJ, and conventional petroleum jet fuel or CPJ. All the results are shown using energy allocation for co-products of biofuel pathways. Higher emissions of STJ pathways compared to CTJ pathways is primarily due to high energy requirements in pretreatment and hydrolysis steps in the STJ pathway. Moreover, STJ pathway outperforms the HRJ, FTJ, and CPJ pathways for all the cases. These results show that biochemical conversion of switchgrass to jet fuel via co-fermentation is a potential pathway to lower GWP 100 of biojet fuel production. Based on all the estimations of GWP 100 for different aviation fuel pathways, it is concluded that the STJ pathway via co-fermentation has lower GWP 100 impact compared to other fuel pathways except CTJ. An increase in AB yield by 15% can reduce the GWP 100 of the fermentation step by 14.4%. Moreover, the most sensitive parameters in the entire life cycle of the STJ pathways are natural gas in pretreatment and distillation steps. When it comes to material input, ammonia in both switchgrass farming and conversion is sensitive to change in ABE yields and contribute to GWP 100. Finally, the novel co-fermentation process has the potential to improve the fermentation process feasibility and provide potential environmental benefits with emerging biojet fuel pathways. This work is supported and funded by USDA NIFA South Central Sun Grant Program, USDA NIFA Project, Oklahoma Agricultural Experimental Station. Also, authors would like to thank Dr. Vijay Gopal Kakani for providing information about switchgrass farming. Thank you. For more information, please contact Dr. David Lampert, an assistant professor at IIT Chicago, and Dr. Hassan Kayatiye, a professor at Oklahoma State University.